As we wrap up our unit on atomic structure, we're going to talk about relative atomic mass. How do we get that average mass that's on that element notation on the periodic table? Well, one of the things we need to be aware of is here that elements come in different flavors, as it were. They have different isotopes. And isotopes are elements that have the same number of protons but different numbers of neutrons. So hydrogen comes in three common isotopes. The isotope with no neutrons, one with one neutron, one with two neutrons, and so their masses are going to be 1 AMU, 2 AMUs, and 3 AMUs, relatively speaking. That third isotope, another way you can write isotope notation is to write the element out with the number on the end. That number is always going to be the mass number when it's written on the end like that. So that is a hydrogen with one proton and two neutrons with a total mass of 3. Here we have two isotopes of helium. The first one has the same mass as one of the hydrogen isotopes, difference being the hydrogen is 1 proton and 2 neutrons. The helium-3 is 2 protons and 1 neutron. And then down at the bottom we have two isotopes of lithium. The one on the right would be lithium-7. That mass number again is 7 protons plus neutrons, and the total number of protons is 3 protons. All lithiums have 3 protons. And then we look on the periodic table, we have that atomic mass, which again we've said is the average of all the isotopes. But that's a funny kind of average there, right? If you've got 3 isotopes of hydrogen, one has a mass of 1, one has a mass of 2, one has a mass of 3. We add them all up, 1 plus 2 plus 3, divided by 2. We should get an average mass of 2 AMUs, but instead we have this number 1.00794 on the periodic table. Well, that's because it is a weighted average. It takes into account the relative abundance of those particular isotopes, and you find when you take a sample of hydrogen really from anywhere in the universe that an overwhelming majority of the hydrogen that we have collected is hydrogen 1. 99.99% of hydrogen in the universe is hydrogen 1, and so that relative mass comes out to be fairly close to 1. Let's look at how this calculation works. So here we have in front of us the isotopes of carbon. All carbons have 6 protons. So here's carbon 12, 6 protons, 6 neutrons. Carbon 13, 7 neutrons. Carbon 14, 8 neutrons. Again, overwhelming majority of carbon in the universe is carbon 12. There's a trace amount of carbon, or there's a small percentage of carbon 13, just over 1%. And a trace amount, 1 in 1 trillion carbons, is carbon 14. Although that carbon 14 is really, really important because every 5,730 years, that carbon 14 breaks down radioactively, and you'll have half as much. It's called the half-life. So carbon 14 is a radioactive particle that we use for radiometric dating of organic compounds. So typically what's going on is that you are constantly exchanging the amount of carbon in your body as you breathe. Breathe in oxygen, breathe out CO2. And so you're constantly, through respiration, you're changing, or I should say you're not changing, you're keeping a stable amount of carbon in your system. And so that 1 in 1 trillion is pretty constant, right up to the point where you take your last breath. And if they bury a body and then it's dug up thousands of years later, what we can do is we can date that organic material, because once it stops exchanging carbon with the environment through breathing, what's going to happen is that carbon 14 is going to break down every 5,000 years by half. And so you can measure the amount of carbon 14 left in, say, a fossilized bone, and then we can figure out how old that material was. Okay, that said, carbon 14 is not really important to the mass of carbon. It is a weighted average mass of the naturally occurring isotopes when we take an atomic mass. And so what we're going to do is we're going to take the mass of each atom times its percentage converted to a decimal. And so here we have the atomic mass in AMUs of carbon 12. Notice it's just a little bit less than you would expect from 6 protons and 6 neutrons. You would expect it to weigh 12 AMUs. But there's something called binding energy in the nucleus that actually a little bit of that mass is converted to energy when they bind together. And so those measured masses are always a little bit less than you would expect them to be. And then we have 0.011% for the percentage of carbon-13 times the mass of carbon-13. And so if you add those two things together, you're going to get 11.855. You're going to get 0.142703. We need to track for sig digs here. Oh, yes, we will. We're going to measure sig digs in this calculation. So we have 5 sig digs in this measurement. We have 3 sig digs in the percentage. So that answer ought to have 3 significant digits. I'm going to underline that third significant digit, 1, 2, 3. The 0.011% or 0.011 has 2 significant digits. The mass has 5, so we're going to underline the 4 as our second significant digit. And then when we add those two things together, we're going to put both of those numbers into our calculator, but then addition is about place value. And since the 10th place is the furthest digit to the left that I have an estimated digit, my final answer there needs to be 12.0 AMUs. And so if you look on the periodic table, lo and behold, you should find the average mass to 1 decimal place, or the atomic mass to 1 decimal place of carbon is in fact right there at about 12.0. How do we detect and know how many isotopes we have in order to take these measurements? Well, in order to detect isotopes, we use what's called mass spectrometry. And a mass spectrometer is, again, here's the machinery as it's set up on a tabletop in a lab. You're not necessarily going to know what all of those bits and pieces do, but they essentially break down like this. This animation's a little rough because my skills are still developing, but we can still talk about the pieces and parts here. So the first thing you have inside the machine is the injection port. You're going to take your sample, usually dissolved in some solution. We're going to inject it into the machine. And then there's going to be a heating coil. That heating coil is going to flash vaporize your sample into a gas. Then here we have some kind of an electron source. And what that's going to do is it's going to shoot super high energy electrons, which are going to, like shoot and pool, are going to knock electrons off your atoms and charge your particles. Again, it's important to have charged particles. Otherwise, it's really, really hot. It's really, really difficult to measure them. So charged particles respond to magnetic and electric fields. So the first set of electric fields that you have here are going to be accelerating plates, which are going to cause those charged particles then to move really, really fast in this direction. And then we're going to set up a giant magnet, which is going to deflect the particles. Now, here's the deal. Since all of the ions in this sample, right, so we injected an element into the system, we shot it with electrons to ionize it, to kick some electrons off it. We accelerated it really fast at this magnet, and the magnet's going to cause it to bend. It's the way the magnetic field is set up. And when it bends, the light particles are going to bend a lot. Think about kicking a volleyball. Okay? You apply a force to a volleyball, it's going to move pretty easily. But the heavy particles, think about using the same force to kick a bowling ball. If your foot's not broken, that bowling ball is going to move in a much different way than the volleyball did. So the light ions are going to bend a lot. Heavy ions are going to bend less. If there are 3 isotopes, you're going to get 3 separate beams. And then you have a detector here. The detector here is going to detect where on this charged plate the isotopes hit. The further to the right they hit, the heavier they are. The further to the left, the lighter they are. And how often those charged particles hits tells me about percent abundance. And so here's what a mass spec might look for something like silicon. So the mass spec readouts actually tend to look like these peaks. A computer program will actually break the peaks into these lines that are going to tell us what's the charge to mass ratio. As long as we set the charge to +1, then these are essentially the masses of the isotopes. This is 28 AMUs, 29 AMUs, and 30 AMUs. The height of these lines, or the heights of the peaks, tell you the percent abundance. And then we have here the computer program has actually gone and sorted all of that out. 92% of your silicon is 28, 4% is 29, 3% is 30. Then you can take these numbers, take your percentage times your mass, your percentage times your mass, your percentage times your mass. And you should get, when you do that work, the atomic mass of silicon. So again, let's work it out together. You're going to take for your atomic mass the percent abundance of isotope 1, which is isotope 28, the percent times the mass of that ion, which is 27.97693 AMUs. Mass of silicon 29 times, the percent of silicon 29 times its mass, and the percent of silicon 30 times its mass. And if you set up that equation, you should end up with this. And so what you should do now is grab your calculator. You should calculate this atomic mass, see if you can figure out how many significant digits should be in your answer, write down that mass, and then unpause the video. So the smart way to do this, because you're going from multiplication to addition, is do it in 2 steps and track your significant digits along the way. We have 4 sig digs in the 92.21%, and we have 5, 6, 7 significant digits in the mass. And so you're going to end up with 4 significant digits in that answer. Our other 2 isotopes are both going to have to be rounded to 3 significant digits because there are only 3 significant digits in the percentages. And if you do the math and write them all out, you should get your estimated digits to be in those places. So again, it's really important that you track this process from the multiplication step to the addition step and write everything out. Write down the whole number that your calculator gives you, or at least 1 or 2 digits past your last estimated digit. Underline where it's supposed to be estimated. And then check place value. Hundreds place, thousands place. So I'm going to round my final answer to that thousands place. I have a bad answer in my slideshow. That should be 28.11. I rounded up prematurely. So 28.11 AMUs. And now check your periodic table. To 2 decimal places, the periodic table, or the element symbol there, says 28.09. So different sets of data are going to give you different atomic masses. So if you use different periodic tables, published at different times, after or published from a different set of data, remember our last digit is estimated. So my 28 point should be again 28.11 AMUs there is really only 2 digits off from the estimated digit here, which this one rounded to 2 significant digits would be 28.09. So we're still within that reasonable error for estimated digits. I'm going to leave you here with the data for the percent composition, the percent composition of sulfur and the relative masses of those sulfur isotopes. Here we have 4 isotopes, so you should go through. You should calculate those isotopes. When you're done, all you got to do is check the periodic table to see whether or not you got it right. As far as the sig digs go, you're going to have to track that through the problem. Hopefully you can sort that out. And again, if you check the periodic table, you should be in the neighborhood of that. Okay? And that is how you do relative atomic mass.